Okay, let's start, and we are getting closer to the real size of the cohort. I think it's half of this. By January, it will be half of this. Good. So today is actually already one of the climacti, I don't know, one of the high points of this whole thing. Because we are leaving what we've done so far in terms of familiar terrain. This is what I want. So far we obviously established probability theory, which is which I assume was basically all familiar to you, and then we started with statistical inference. And last time we did maximum likelihood estimation, which I think all of you also have heard before. And the stuff today and next week, maybe that's actually new to most of you. And it's actually also very statistic-key, if you want. Definitely frequentist statistic-key. Because the question is, how good are estimators? And that's an important question in statistics and in machine learning and data analysis and whatever, because it's fairly straightforward to come up with an algorithm that turns some data into lower dimensional other data. So for example, I don't know, come up with a classifier that then if it is trained, allocates a new value to some data point, so it says it's this class or that class. It only gets interesting if you ask the question, so is this actually doing a good job? And of course this question about doing a good job also applies as in predictive analysis, also applies to inference problems. And today we want to talk about finite sample estimator properties, essentially when the sample is of a fixed size n, so you have, I don't know, 1,000 data points, you have 1,000,000 data points or something like that. And next time the question is what happens with estimators and their properties if you allow for the sample size to go to infinity, so these kind of limit questions. And yeah, so essentially coming up with estimators, you can also just come up with them by just guessing and just saying, okay, we want to do this. Then the question, so we want to square everything, write it on paper, cut it out, send it to our grandmother, and she then comes up with a random number, and that's your result. If that is a procedure that works and that has some good properties, why not do it? So coming up with new algorithms, with new estimators, is kind of only half of the deal. The bigger question is then, are these good procedures? And what we're doing today, again, based on finite samples, this is based on these kind of chapters. Yeah, read them. I found all of them, especially the Wassermann and the Held and Bore, they're good, they cover certain aspects, but they constantly switch back and forth between finite sample properties and limits. And I decided it's easier to first deal with the finite case, which is maybe a little bit simpler because it requires less kind of limit aspects. Obviously, and then do the limit in a separate session. So they switch back and forth, but cover everything, of course. And I got most of the stuff from here. And de Gut and Scherwisch, they do this Kramer-Rao bound, which we'll do in the end quite nicely in this section. Okay. So before we talk about now what are good estimators, I would like to emphasize the frequentist sampling intuition, because that's basically the intuition that lies below all of these questions of how good estimators are, because in terms of estimator quality, we of course look at expectations, or the questions of how good are these procedures on average over many times of applying them. And because I think so far we haven't really inhaled the frequentist sampling intuition, I thought it would be good if I first introduce this before we then, based on this intuition and armed with this intuition, talk about the criteria for good estimators that we want to cover today. So I assume that you are familiar with this, but I nevertheless wanted to put it into the notation that we use here. So for everything that we do we assume that we have a parametric statistical model, and we are looking at n data points. And remember that these x1 to xn, they also can be vectors. Yeah? So x1 can also be a random vector. So if you have multidimensional data, so let's say 10 data features per data point, then this would be a 10-dimensional vector. And then if you have a million 10-dimensional data features, this x1 to xn can be pretty big. Yeah? So don't be fooled by the fact that it doesn't say big data in flashy terms here. It can be big data. And these statistical models, these data points, of course, are assumed to result from the realization of random variables, and they are supposed to be distributed according to some probability mass function or probability density function. That's what we have established. And of course, this is what I always implicitly assume is clear to everyone, and I hope it really is, that if you have observed data, so if you have an observed data set that you now inquire from with what it is, what are you doing, SQL to get some data out of some, to write some code to get that out of some data bank or so. Are you doing something like that in data science? Yeah, good. So this real observed data, this is then considered one possible realization of these random variables. Yeah. So this is always the kind of additional depth that statistic brings to the table. Yeah. So with Tim, you go to the data bank and download the data. That's the data. And with me, yeah, that's the data, but it's a realization from all of this. No, I just got this cable from Tim. Although without Tim, this lecture wouldn't happen because I wouldn't have any power. So now about the sampling perspective, and specifically the frequentist perspective. From the frequentist perspective, yeah, we have this observed data as one possible realization of this, but, and this is the important thing about the frequentist perspective, we have a probability distribution over these random variables modeling data points, and we can imagine sampling repeatedly from that. You don't do that. Usually you have observed data, and that's the data, but from the perspective of the model, which specifies a probability distribution, you can sample again. So here this would be one sample, so with small x I denote the realizations, and you have n data points, and this is the first realization of these n data points. And then of course you can, like we established last time, compute some estimator on this. For example, you compute the mean of all these data points. Again, these data points can also be vectors, then you compute the mean over all these vectors. Yeah? That would be one sample. But now you can, from the perspective of the probabilistic model of statistics, you can sample that again. And then you again can compute, for example, the sample mean. And then you can do it again, and you can do it again, and you can do it again. You can do it infinitely many times because that's the assumption of the model. And then what I want to emphasize here is that for each of these data realizations, again, in real life you only have one data realizations, but for these imagined data realizations, you can compute, for example, the sample mean or any kind of statistic, and these then also have as many realizations as there are data points. And the question of frequentist statistics is essentially what is the distribution of, for example, the sample mean, or what is the distribution of more general statistics. And of course, this distribution has a lot to do of a given statistic with the distribution of the data. So if the data have a specific distribution, then of course something that you compute on the data, so you apply a deterministic function to the data, has a distribution that is in some way related to the data. depending, of course, on what the function is. If the function is just neglect the sample and just always take 2 as the estimator for everything, then of course the distribution will just be a Dirac delta measure on 2. So it's 2 with probability 1. But yeah, so that's the question. So for what we're now looking at are distributional properties of estimators or statistics. So remember, statistics and estimators are just functions on the data. The kind of difference is that estimators map into parameter space. So they, of course, try to estimate parameters, and that means they have the same dimensionality. Statistics, like the t-statistic, for example, doesn't necessarily map into parameter space. Yeah, that was the example. And what we are concerned with today is the distribution of estimators for fixed n. And this is also what's shown here. So this was under the assumption of a fixed n. So always keep in mind that n is, in this setting, not the number of realizations that you draw from the probabilistic model, but it's the number of realizations that you draw for one realization if you have independent data. Yeah? So don't confuse that. And then next time we want to ask what about the distributions of parameters if n is allowed to go infinity. So if for each of these realizations we let n go bigger and bigger. So are there questions about this sampling intuition? Because that's really important and underlies everything. You usually don't find that much discussed, but it's fairly important. That's all clear? No questions? Good. Good. Then based on that, we now want to discuss a number of properties. And the first ones would be error bias and unbiasedness. Which have to do with expectations. Then we talk about variance and standard error of estimators. And then we talk about the Cramer-Rao bound, which is a lower bound for the variance of estimators, so that relates to variance. And finally, we talk about mean squared error as a kind of criterion for estimators that involves both biases and variances. For some reason, machine learning likes mean squared error. You always find the bias-variance decomposition. You find that in machine learning books for whatever reason. There are reasons, because you can basically trade a little bit of bias for variance. So it's an interesting criterion. But on the other hand, machine learning books usually don't discuss things like Cramer-Rao bound, but focus on mean squared error. Maybe you have better reasons why than I. Good, then let's get started. If there are no questions, so error bias, unbiasedness. So most of the stuff is actually in kind of theorem definition form, which means things are quite simple and you just need to memorize what these definitions are, and then you're all set. So there's not that much to understand. Of course, there are things to understand, but it's not that conceptually hard. So what do these terms refer to? Error, bias, and unbiasedness. We always assume, and this will be in most of the definitions and theorems, we always assume now that there's a parametric statistical model, that it has a probability mass function p theta. We always assume that we have n random variables modeling our n data points, again, can be vectors or scalars, and that these derive from this distribution. And we always assume that there is an estimator for theta, and like last time we write this as a function of x1 to xn, and we don't write the whole thing out, or whether it's now a function. So of course, you know, if you compute a sample mean, you compute that on the realized values, but in theory, because the realized values are random variables, you compute that on the random variables that are behind the data. So this is what we will assume all the time, so I will not discuss that, although it will always be mentioned. Yeah, no. If there are questions, interrupt me. So then about these terms, error bias and unbiasedness. So first thing that one can define is the error as the deviation and that's important that you now get used to what this theta without anything means. So remember last time that we talked about that there are true but unknown values of the parameters, and the theta without anything is now always a representation of the true but unknown value, but allowing for the fact that the true but unknown value can be any value in the parameter space. Yeah, so you should always think that for a fixed theta in parameter space, one looks at different things. For example, the error, and the error is just defined as the difference between an estimate. So here you evaluate an estimate based on the random variables and the true but unknown value. So whenever you, for example, use the sample mean to estimate the expectation, if you take a sample and you know the expectation because, for example, you simulated that, as I like to recommend, you can look at, so you maybe simulate from a Gaussian with an expectation of 2. You take 10 samples, compute the sample mean, get 2.1, then your error is 2.1 minus 2, 0.1. Fairly straightforward, but of course always tied to a specific realization. Now the bias of an estimator is not tied to a specific realization because it's the deviation between the expected value of the estimator from the true but unknown value. Yeah? And the expectation here in the sense of these realizations, yeah. So you have you can think that you can sample in principle such a probabilistic model many times, and then you would have a distribution of estimators, and they would have this distribution, of course, would also have an expectation. And the way it's written here is so it should be the expectation of this estimator, and this little theta here is meant, what this is supposed to represent is that you compute the expectation with respect to the data distribution that is governed by this p theta, so this true parameter. And so of course, if you change the true but unknown parameter, so for example, if you have a Gaussian with expectation 0 and you compute the sample mean, then roughly this will always come out 0. If you have a Gaussian with mean 10, with expectation parameter 10, then of course the mean will come out around 10. The expectation of the estimator and hence depends a lot on the true but unknown parameter, but what is important is the difference between the expected value with respect to the true parameter and the true parameter. Yeah? Yeah, I write this here with this B for bias, which will come up later. And now a parameter estimator hat theta n is called unbiased if the bias is 0 for all n. Yeah, so it's also, and so it's relatively easy to understand, okay, if you have a lot of data points, this might happen, but this is not so much the point here. The point is that also for a few data points, the expected value of the estimator is the same as the true but unknown value. And this is supposed to hold for all possible values of the parameter and for all possible numbers of data points. And if this is not the case, so if this doesn't hold for all n and for all theta, then this estimator is called bias. Yeah. So the error depends on the realization. As I said, the bias is the expected error. So yeah, you can also view this here as the expected error. So if you put the expectation around this thing, then of course, because this is a fixed number, then you and with the linearity of expectation, you get this. So the bias is also the expected error. Yeah, is that idea clear? Then let's, so if there are no questions, then let's look at an example immediately to look at what that really means. And yeah, again, this E theta means expectation with respect to P theta. It's a little bit So what you, in a way, need to get used to there is that this p theta is, of course, a distribution over the data. And if you're now supposed to compute the expectation of the estimator, then you have to first think, how does the estimator transform the data so that I can use this probability distribution to evaluate the bias. Hence, this is why I'm so after transformations of random variables. Because this is again one of these problems. So first example, namely here in theorem form, the unbiasedness of the sample mean and the sample variance. So here we assume we have a parametric statistical model, again with our sample and our PMF or PDF. And we define mu to be the expected value of one of these random variables, and we define sigma square as the variance of one of our xi. Of course, if we say this is a random sample, that means that they are IID. That means they all have the same expectation, they all have the same variance, and they are independent, of course. Don't confuse this scenario with anything Gaussian. We are not saying anything about Gaussians here. So this mu here and the sigma square are not Gaussian parameters. They are just short symbols for the expectation of one of the random variables and for the variance of one of the variables. Yeah? Now let this be the sample mean, and this is we looked at the sample mean previously, but we never really formally introduced it. So now let me formally introduce you to the sample mean. So the sample mean is this random variable which you get from adding up all the random variables here in the random sample and dividing by the number of random variables. And then because these are random variables, and you do basically you sum some random variables and you apply a scale a multiple to it, you get again a random variable. And the statement here is that the sample mean, so this random variable is an unbiased estimator of the expectation mu, so of the expectation of each of the xi. And the next claim is that the sample variance, which we define as the squared deviation between each random variable and the sample mean divided by n minus 1 or multiplied by 1 over n minus 1, that this is an unbiased estimator of the variance sigma square. Do you remember how the maximum likelihood estimator for the Gaussian variance looked in relation to that?
Just 1 over n?
Exactly. Yeah. Exactly, and from this you can already, and this will come up multiple times, infer. So if this is unbiased, and this is an unbiased estimate of the variance, then the maximum likelihood estimate of a Gaussian cannot be unbiased because it's divided by 1 over n. But we'll come back to that. Now the question is, why does that hold, and how does one show that? Well, we need to evaluate the expected value of the sample mean. And here I drop the subscript theta, mainly because I didn't have it on the slide earlier, and then it was easier to write for ease of notation. We set this rather than putting the theta in everywhere. So we compute the expectation of the sample mean with respect to the true but unknown distribution parameter of the data. So that means we put in the sample mean, and then we can use the properties of expectations that we established early on. So because these are linear, we can basically move the expectation under the sum sign. And then we here have our expectation xi, which we call mu, and then we are summing up mu here n times. So we have n times mu, which we multiply by 1 over n, and then we get mu, which means that the expectation of the sample mean is mu, and that means that the bias, so the difference between the expectation of the sample mean and the true expectation, is 0. And this holds, again, regardless of any Gaussian stuff. This holds for all kind of distributions that the data can have, and of course under the assumption that the expected value or the expectation exists, so that this is a finite value. Oops. For the variance, to show the variance, we first do actually, to show the unbiasedness of the sample variance, we actually first look at the variance of the sample mean. We will probably define the the variance of the sample mean in a second, but we need it already to show the unbiasedness of the sample variance. So let's look at the variance of the sample mean. Well, that's the variance again of the sample mean. Then we can use this property that if we multiply something, then we can take that out. We can and need to square that. We can here write the variance of the sum as the sum of the variances because we assume independence. And then we already are in a scenario where we know this variance, namely sigma square. Again, we end up n times sigma square, and then we get rid of one of this 1 over n square, and find that the variance of the sample mean is sigma square, so the true variance divided by n. And then to actually go for the unbiasedness of the sample variance, it's a little bit more involved. So one needs to actually show this equality. So if you have this term here, which you of course have in the sample variance, you can, of course, without changing anything, subtract the true expectation at the true expectation, and you can rewrite this like this. And this requires a little bit of algebraic manipulations, which I didn't include on the slide because it gets a little bit too tedious. So you basically would have to, and the reason why it's a little bit tedious is because you have to evaluate this, reformulate it, and then you get to this. So that's a nice homework exercise. But it is not conceptually interesting. But if you appreciate this, then you can compute the expectation then. So if we look here at the sample variance and we compute the expectation of n minus 1 times the sample variance, then we look just at the expectation of this because this n minus 1 goes away immediately. Then we replace this by what I've just showed you with the algebraic manipulations. Here you can then put in the expectations, and then you already end up with the variance, namely the variance of the data and the variance of the sample mean. This is why we needed to compute this. And then you get to this and end up with n minus 1 sigma square. And then if we, so this was the expected value of n minus 1, the sample variance. And then if you focus on the pure sample variance, then this is of course 1 over n minus 1 times s square. Again, you can get this out, have here the variance, and I think this should still be just an S. I think that's a typo. So go over this again. It's not as easy as the unbiasedness of the sample mean. So to show that the sample variance is unbiased involves a little bit more of not linear algebra, of algebraic manipulations. But it still, as you can see, can be done on 2 slides. And this is no, sorry. Now I confused myself. That's not a typo. This is the expectation, putting that in. Then you get here variance, and this is just the final thing because they cancel out when you see that the expectation of the sample variance is the true variance. Yeah. So that's the unbiasedness of the sample variance. If you want, you can also see this already as a proof for the biasness of the maximum likelihood estimator for the variance of a Gaussian. So yeah, so that was the unbiasedness of sample mean and sample variance. Are there questions about this? So what this means is computing a mean is always a good thing in terms of unbiasedness to evaluate the expectation of the random variable from which you think your data are modeled, and computing the sample variance is always a good thing to estimate the variance from which your data arise. Yeah? So computing means and variances makes sense under these assumptions. Any questions? No? Then the next thing is something of interest maybe for some, namely the biasness of the sample standard deviation. So I assume you know what the sample standard deviation is. So again, we assume we have this model and we have the variance of each of these random variables. And now we define the standard deviation as the square root of the variance. Yeah? So standard deviation, like variance, being some analytical theoretical quantity. And we're not talking about the sample standard deviation, which is the square root of the sample variance. Yeah? Now the sample standard deviation, which definitely psychologists are very familiar with, because that's what you essentially get taught to calculate in undergrad statistics. The sample standard deviation is actually a bias estimator of the standard deviation. So to use the sample standard deviation as an estimate for the standard deviation is at least biased. The thing is, the good thing about these biases of variance, and for example in the Gaussian case and of this, is that these biases that these estimates are usually asymptotically unbiased. So if n gets very large, these biases go away. But for relatively small data sets, like 10 to 30 participants or something, these biases are still there. So the question is, why is this biased? And this essentially follows with Jensen's inequality and the fact that the square root is a concave function. So basically applying Jensen's inequality shows then that the standard, the true standard deviation, so the standard deviation is actually larger than the expected value of the sample standard deviation. Yeah, so if you haven't, what this also shows a little bit more generally is if you're an unbiased estimator and you now apply some nonlinear transformation of this, so remember that the sample variance was unbiased. If you apply a nonlinear transformation, in this case the square root, there's no guarantee that this again will be an unbiased estimator of the thing that you're then trying to estimate. So it's a little bit subtle, but I also found it quite revealing, because one is very used to computing standard deviations from data and not necessarily aware of the fact that this is actually a bias estimate. Of course, biased for small n. If n gets large, this is what we'll discuss next time, these things are asymptotically unbiased, so you're fine again. Good, this is already what I wanted to say about error, bias, and unbiasedness. Any questions? Who has heard the term that this is an unbiased estimator before? No? Also not in machine learning? No? Because of course in machine learning, if you estimate some parameters, or you I don't know, use gradient descent to find some parameters, fit some parameters, the question is also how good these are, and then people also discuss biasness of these estimates, of course if they have a probabilistic model of the whole thing. Good, then before the break, let's introduce variance and standard error for estimators. That is, of course, you know what variance and what the variance is already, but now we're defining it just for estimators. So again, we assume that we have a parametric statistical model with a specific PF, where the random variables are distributed according to this, and we have this estimator. Now, the variance of an estimator, so we're talking about the variance of an estimator, is essentially just defined as the variance of this random variable theta hat n And you know that the variance of a random variable is defined as the random variable minus its expectation squared and the expected value of that. I mean, it's just the variance, as we are familiar with it. Now, the only maybe subtle difference here is that the expectation are with respect to the true but unknown parameters. But besides that, that's it. And the standard error of the estimator, or of an estimator, is defined as the square root of the variance of an estimator. Yeah. So I think the only important thing here is to appreciate that we're talking about the variance, if you want, the variability of estimators. But then this variance of an estimator is just the variance of the random variable estimator, and the standard error, well, it's defined as the square root of that. Actually, there are, if you go over these three books, they actually have conflicting definitions of these terms. I think specifically the Held and Bove deviates from that, I think. Anyway, this is, I think, the stuff that you find most generally. And I actually don't know right now what kind of conflicting definitions they have. I think sometimes the standard sometimes the standard error is defined as the square root of an estimate of the variance of this. I think that's the clash that you sometimes see. So sometimes the standard error, instead of being defined as this analytical entity, namely the variance of the estimator, it's defined as the square root of an estimate of the variance of an estimator. But we are fine with that, and this seems to be the more common definition. Yeah, and this is also the standard error is, of course, the standard deviation, because the square root of the variance is called standard deviation. Yeah, and everything, all the expectations, variances, and standard errors are always with respect to p theta. Here then an example, if there are no questions to this. The example would be computing or evaluating the standard error of the sample mean. So again, we assume our parametric statistical model. We write the expectation of one of these random variables as mu, the variance of one of them as sigma square. And then the claim is that the standard error of the sample mean, or also known as the standard error of the mean, is given by sigma, so the square root of this divided by the square root of n. That's the claim here. I think this formula is familiar to psychologists at least. So how is it derived? Well, we've seen already that the variance of the sample mean is sigma square divided by n, and then it's just a question of taking the square root. And then the square root of sigma square is sigma, and you have to, of course, do it in the numerator and denominator, and then you're already there. So very simple if you know what the variance of the sample mean is. And the variance of the sample mean is not, and this is maybe something to remember here, the variance of the sample mean that we already introduced earlier is related to the variance of each of these random variables, but it's actually smaller because it's divided by n. Now you can estimate the standard error by taking the sample standard deviation and dividing that by square root of n. So this is what in psychology you often do to compute the standard error of the mean. You would use the sample standard deviation and divide by the square root of n. And this is, of course, an estimator for the standard error. It's, however, also biased, specifically for a small n, because we've already seen that the standard deviation is biased. Yeah? And the square root of n doesn't do away with the bias, which one maybe would have to prove. Yes? No, not really. I mean, it's just taking out of the expectation, so there's not much to prove. So here's another example, the standard error of the Bernoulli parameter maximum likelihood estimator, because why not? So here we assume now that the x1 to xn are distributed according to the Bernoulli distribution, and we have as mu L the maximum likelihood estimator for mu. Does anyone remember the formula for the maximum likelihood estimator for mu, for Bernoulli random variables? Guess, have a guess. So Bernoulli random variables come out 1 and 0. You have n of these coming out 1 and 0, and you're supposed to estimate the probability for them to come out 1, because that's what mu does. So let's assume you have 10 observations, and you have you observe 4 times a 1 and 6 times a 0. So what's your estimate for mu? Have a guess. Come on, that's easy. If you have a coin and you throw it and it comes out this 5 times heads and 5 times tail, what do you estimate is the bias of this coin? Hmm? 0.5. Yeah. And how did you get to the 0.5? Exactly. So so the sample mean actually is also the maximum likelihood estimator, like for the Gaussian, for the Bernoulli. Yeah. So remember, the maximum likelihood estimator for the Gaussian expectation parameter is just the sample mean, and also the maximum likelihood estimator for the mu here is the sample mean in terms of the Gaussian. And now we're interested in the standard error of the of this maximum likelihood estimator, and the claim is that it's given by this. This is shown here, which also, of course, then involves the variance of the Bernoulli random variable, because the standard error is defined as the square root of the variance. So what's happening here is we start with the standard error defined as the square root of the variance. We put in the maximum likelihood estimator, which we just rehearsed that this is actually the sample mean, and then we account for the fact that we multiply with 1 over n, and so we have 1 over n square outside. We have the variances of the xi, and then we have already established in lecture 5 that the variance of a Bernoulli distributed random variable is mu times 1 minus mu. And then we can plug that in, and then we cancel one of the ends out, and then we are already here. Yeah? And again, we can estimate this standard error by plugging in the maximum likelihood estimate. Yeah? So that would then be an estimate for the standard error. It's a kind of natural estimate to use, but we are not saying anything about whether it's a good estimate or not. Yeah? So it's based, of course, on the intuition that an estimate for mu is the maximum likelihood estimate. So why not estimate the standard error of this by this? Because of course, in general, if you know that the standard error or the variance of an estimator is something and it depends on a parameter, then it doesn't really help you much, because you don't know the parameter. So you need an estimate of the parameter to actually say something about this variance. Good. And this is a good time for a break, because we now established the main concepts, so error, bias, and biasness. Variance and standard errors of estimators, looked at a few examples, and the next thing then is kind of a interesting and famous theorem about the variance of estimators, because the question is, what are good estimators? And of course, unbiasedness is a good property, at least asymptotically unbiased, but unbiasedness for all m is of course even better. And if you have an unbiased estimator, and assume you have like 2 unbiased estimator for something that you came up with, so one of them you derive the maximum likelihood, and the other one you came up yourself somehow randomly, and they are both unbiased. And the question is, which one should I now choose? And then a not sure thing is, of course, to say, well, I choose the one that is less variable, so that more reliably over many repeats comes out with values closer to the truth, and this is what Cramer-Rao bound is all about. Yeah. So any questions now? Otherwise, let's take a break and continue 11:15. Hello. Yeah. Good. Now the next thing then is to look a little bit more into the variances of estimators, which the Cramer-Rao bound is about. And the fundamental idea here is, of course, if you have multiple estimators, as I said, which are unbiased, then taking as a way to estimate parameters is, of course, a good idea to take the estimator with the smaller variance. So essentially having small estimator variance is a good thing. It's relatively intuitive because the error on a given realization is on average smaller. Now the Cramer-Rao bound defines a lower bound for the variance of unbiased estimators. So the first thing is that it applies only to unbiased estimators. So if you have a biased estimator, this whole thing doesn't apply. Then it gives a lower bound, meaning that the variance of an estimator is equal to or larger than this lower bound. Now, if an unbiased estimator actually takes on this lower bound, then this estimator has the minimal variance among all unbiased estimators that might have a larger variance. So an unbiased estimator that takes on the Cramer-Rao bound is optimal in this setting, because in general, in math, obviously you want to know what is best, and then the question is, what does it mean to be best? Here one thing is that if you have this lower bound and then you have an estimator that actually takes on this lower bound, then that's good, and that's in this sense then optimal. But there are more optimality criteria for estimators that also take into account this limit stuff that we will discuss next time. So yeah, you can say that an estimator taking on the Cramer-Rao bound is optimal, but that's only optimal in a certain sense, of course. Then the Cramer-Rao bound rests on the notion of expected Fisher information, and we briefly discussed Fisher information last time when we talked about Fisher scoring, but today we talk about that more and have a better definition, or a cleaner definition, let's say, and we will also see Fisher information in the rest of the course again and again, so it's also kind of a helpful definition for the remainder of the course. Then the results that around the Cramer-Rao bound, they hold under the so-called Fisher regularity conditions, which are a number of conditions that need to be fulfilled for this whole thing to hold, and these are of course mathematical conditions, and these are kind of one can of course express these regularity conditions even with more mathematical rigor, but one can also express them like this, so that we not only say, okay, they hold under certain conditions, but we express the conditions, but we now don't go too deep into what these conditions are. So one thing is that all these results that follow under the assumption that the parameter space is an open interval, so that the parameters cannot assume values at a parameter space boundary, that the support of the probability mass or density function governing the data does not depend on theta, so that for example, if you have, for example, a uniform distribution from 0 to a parameter theta, then of course this the support of the so where there's non-zero probability depends on the parameter, so this is not allowed, and you find in the books, you find then always like counter examples where this thing breaks down. That's not too helpful because these are things that you rarely encounter in practice, because these are of course the things that are ignored because they are counter examples, and yeah, I don't enjoy studying them that much because you always feel like, yeah, now I've learned something, but I will never use it. Well, you have learned something. Then this needs to be identifiable models. So if you have two probability density models that have different parameter values, they need to be different. So assign different probabilities or probability densities to data. The likelihood function is twice differentiable. You already need that for the definition of expected or Fisher information. And then what we will need a lot in the examples is that you can, if you have a differentiation operation, so computing a derivative under an integral sign, that you can take this operation outside of the integral, or you can take that, or the other way around, you can take a differentiation operation into the integral. And these, of course, are fairly subtle, and also you need a lot of properties for these things to hold. But we here assume that this can be done, and then the proofs actually are fairly straightforward. So these are these Fisher regularity conditions, these conditions under which this holds. But essentially that means for the standard scenarios that we are looking at, like Gaussians, these things are fine. Yeah? Good. Then before we can talk about Kramer-Rao, we now need to introduce and probably define Fisher information. Together with the score function, and once we've introduced Fisher information, we will also define expected Fisher information and observed Fisher information, because all of these, if you read the books, you will come across. So again, the assumption is, like always, we assume we have a parametric statistical model. We have that is characterized by a PDF. We are doing the whole thing just for scalar parameter. You might remember already that last time you get, so if you have multiple parameters, you get two matrices in terms of Fisher information, and we neglect that. So we assuming a scalar parameter. One can generalize all of this. You can read it in the Degroot how to generalize all of this, but the notation and the administrative overhead just gets larger, and I wanted to avoid that. So we have a scalar parameter, data is distributed according to the PDF, and what we now also need to take into account is the log likelihood function. Yeah? So we assume, like we discussed last time, that we formulate a likelihood function and its log, which is then the log likelihood function. So that's the setting, and then score function and Fisher information are defined as follows. The first derivative of the log likelihood function, ln, is referred to as the score function. Yeah? So that's just the definition. If you have a log likelihood function, the n here means that we have n data points, n random variables. Then the derivative of this log likelihood function, of course with respect to theta, because the log likelihood function is a function of the parameter, is called score function. Yeah? So that is just renaming the derivative of the log likelihood function as a score function. We will, in the end, talk a little bit about at least why Fisher information is called information. We will not talk much about why score is called score. So take these names now more as kind of definitions without asking immediately and being completely unhappy if you're not quite clear why this is called score or why this is called information. For the moment, take this mainly as definitions and of terms that are just there, because otherwise you make your life miserable. So again, score function defined as the first derivative of the log likelihood function. If there's only one random variable, then we also drop this n subscript and just say as theta and call this the score function of a random variable. Now, the negative second derivative of the log likelihood function is referred to as Fisher information. So again, log likelihood function here, and now we're talking about the second derivative, so the derivative of the score function, and we put a minus sign in front of it, and this is what we call Fisher information. And of course, score function and Fisher information both depend on theta. So if you put in a different theta, then you have get to a different information if this depends on theta. So often, if you compute the second derivative, the theta is not in there anymore, and it's actually a constant. So we will look at examples for this, I think, in the exercises where people are supposed to compute Fisher information for Gaussians or for Bernoullis. So we will see examples for that in the Übung. Again, if there's only one data point, this is also written as I theta and called Fisher information of a random variable. Now, this is Fisher information. In principle, a function of theta can be that it's constant with respect to theta, because the second derivative of the log likelihood function with respect to theta is just a constant. There are two more things with respect to Fisher information. One thing is its expected value. The other thing is it evaluated at the location of the maximum likelihood estimator. So maybe let's do the second one first. So if the Fisher information, there's a head missing, and there's also a head missing. If the Fisher information is still a function of the maximum likelihood, so you can substitute the maximum likelihood, you can substitute a parameter value in there, and you substitute the maximum likelihood estimate. You call this the observed Fisher information of a random sample. Because what else do you want to do? I mean, if you want to say something about the Fisher information and it's still a function of the parameter, you don't know what the parameter is, your best guess is, of course, the maximum likelihood estimator. So that's observed Fisher information. More important, and what we will see more, is the expected Fisher information, and this is just the expectation of the Fisher information. And there you might be a little bit, or needs to appreciate why this is a random variable in the first place. And there you need to trace it essentially all back to the log likelihood function, because the log likelihood function and the value of the log likelihood function is, of course, for a given parameter, depends on the data realization. So if you, for example, fix one parameter value, let's say first you sample some data, and then you write down the log likelihood, or you evaluate the log likelihood for this data, then it's of course a function of the parameter. But now you assume you look at just for one parameter value and you sample again. Then of course this is a random variable, and hence log likelihood functions essentially are random functions. Hence their derivatives are also random. The second derivatives and the negative of that are also random. And in this sense, you can compute the expected value of the Fisher information. Now, again, this all has to do with the fact that the data is a random variable, which makes the log likelihood for also a log likelihood function a random variable. And so here we have the expected Fisher information. And we already had this notion of the expected Fisher information last time. It turns out that the expected Fisher information is often easier to evaluate than the Fisher information itself. Good. So these are the definitions, and I hope that these definitions work for the rest of the course. I think they work for everything today. I had to go a little bit back and forth through the books to have this clear. One thing is also that this Fisher information for n data points versus Fisher information for one data point. I hope it works. Otherwise, I will at one point go back and revise these definitions. But I think, except for this here, don't do it. For now, they are fine. Now, if we want to establish the Cramer-Rao bound, the first thing and the first properties that we will also see a couple of times are these relationships that are more or less surprising. The first thing, that the expected value of the score function is 0. And the other thing, that the variance of the score function is the expected Fisher information, which is the same as saying that the expectation of the derivative of the log likelihood function is 0, or the expected Fisher information, and equals the variance of the score function. And both of these are very important to establish the Cramer-Rao bound. So they are not interesting per se, but well, they are also interesting per se, but we will need them if we introduce the Cramer-Rao bound, because the Cramer-Rao bound crucially depends on that. And now, to understand where Cramer-Rao bound is coming from and where this is coming from, I have included these proofs, and these actually I want to show you a little bit slower, because if you are happy with these proofs, then Cramer-Rao bound is not a problem. But if you're not happy with these proofs, then it remains a little bit mystic what they are coming from. So essentially, I want to briefly show that the expectation of the score function is 0, and then to show that, well, the other thing I show then. So the question is, why is the expectation of the score function 0? And well, one can just get to that by doing some math, essentially, so doing some calculations. So the score function, the expectation of the score function is of course the expectation under this PDF. Now we're looking only at one variable. We will show that this is for one variable, and because it's for one variable, and because of independence, which one essentially also would need to show, then it also holds for n variables. Anyway, we have here the expectation of the score function with our probability density function. That's just how it is defined. So scream if you're unhappy with something. Now, what is the definition of the score function? Well, that's the derivative of the log likelihood function, which I write here as L theta, P theta x. And yeah, note that the expectation is over x, right? So that's the expectation over data realizations. Because over what else? It cannot be over parameters, because we're not in a Bayesian setting. Parameters don't have probability distributions. Yeah? Then, of course, this is just the log of the likelihood function. And then we can already evaluate, or we have to evaluate this derivative. So the derivative of the logarithm is 1 over x. So remember that ln, I think everybody knows that, but still is 1 over x. And then we need the chain rule. So what we get is 1 over theta times the derivative of L theta. And then we realize that actually the L theta is defined as what? Does anyone remember that? I mean, you see it in the proof, but what is... The what? Production. Yeah, you're right. The product of all the you're right. What we are doing here is actually only for one variable. Maybe I should have stated that a little bit clearer. So because we are not looking at Sn, but we're looking at S, so we only have one random variable, which means we basically have a product from 1 to 1. But then what, so it's the product of what? Yeah, exactly. So that's just the definition of the likelihood. It's just the probability density that applies, or probability mass function that applies to our data. And this is already the major trick here, because then we see that we have one p theta x here and one p theta x here, so they cancel each other out, and we get to d theta L theta dx. A little bit of question of what the x is now about, but of course we know that L theta is with respect is something with x. Now we use the Fisher regularity condition because we had this slide, so why not use it? So we take the derivative outside of the integral. We assume that this is allowed and doesn't cause any problem. And then we again replace the likelihood function with this, and then we have the integral of the of one probability density function, which is obviously 1 because this is a probability density function, and then we have the derivative of 1 with respect to anything, and that's 0. So we have shown that the expectation of the score function for one random variable is 0. It's a little bit of magic, but no, it's not magic. But there are some. The tricks are essentially by realizing the likelihood function corresponds to the probability density function, and accounting for the chain rule. So that's the first thing, and the other thing then to show was that, or other questions here? Doing this here, I think doing this step here, if you are math inclined, you might wonder, can you really do that? But we assumed we can do that, so we are happy. The other thing then was to show that the variance of the score function is the expected Fisher information, so that this holds. And that basically we will, this is what we want to look at next. And there, the first thing to realize is that the variance of the score function is, of course, the expected value, or we can also use the, what do we want to use? Right. Yeah, we can, if we use the variance translation theorem, then we can already, I don't want to fuck things up. So that is the probably that's the expectation of S theta minus E S theta squared. So that's the definition of the variance, and we've just seen that this here is 0. So we essentially are only interested in this, yeah, because the expectation is 0. So the subtracting the expectation and evaluating the expectation means just subtracting 0, and we can just focus on evaluating the expectation of the square score function. And actually, I will work the other way around. So the claim is now that J, the expected Fisher information, is the same as the expected expectation of the square of the score function. Yeah? I think there are signs for that. It's the claim or something. And that's what I would do. Now, also this can be calculated straightforwardly. So again, starting with the definition. So the expected Fisher information is the second derivative of the log likelihood function, so of L theta, which is the same, of course, as the is of ln theta. And what else? Yeah, and then this is of course just taking two derivatives here, so minus d theta d theta ln L theta. That's the same thing. Everything's fine. Sorry. And then here the derivative is of course what we've already seen. Just gets a little bit long. I think I will, once I've shown you that, I will go back to my slide and show you the rest on the slide, because otherwise you'll just have to suffer my handwriting. So we now need to compute the derivative of 1 over L theta because of the log d theta L theta. Now let's go back to the slide, because otherwise it just gets more messy. So we are here. And then you of course need to compute the derivative of a quotient, so you need the quotient rule. So derivative of g, or of f divided by g, is derivative of f times g minus f times derivative of g divided by g square, where you always wonder where's this g square coming from. But that's the quotient rule of the derivative, which is done here. So here you have then, so if you set this to f here in the denominator, and in the numerator you set this to f, and in the denominator you set this to g, and apply the quotient rule, you get to this expression. Looks a little bit daunting, but here you, for example, have the g square. And then you can, so this is just quotient rule, then you can separate these two things and also get rid of one L theta. And then you have these two terms to which you then basically can apply, in a way, similar tricks as we did during computing the expectation of the score function. So first of all, you write out that the expectation means the integral with respect to the density of interest, and then this L theta and this density cancel out, and again the derivative is taken out of the integral. And what is happening here? Not much, just the square is written around this whole thing. And then the first term disappears, because again you have, like we did for the expectation, the integral of the probability density. So this goes away. And you can, this term here, this d theta L divided by L theta, you can rewrite again as d as the derivative of the log of the likelihood function square, and this is just the score function, and then you have the expectation of the score function. So also this is fairly straightforward. Oops, we didn't go out of this. Also this is fairly straightforward. You just need the quotient rule at one point to get there. So these are two things that need to be established to get to the Cramer-Rao bound. So the expectation of the score function is 0, and the variance of the score function is the expected Fisher information. Now, armed with this information, we can actually state the Cramer-Rao bound. So Cramer-Rao bound again works on a parametric statistical model. With PDF or PMF P theta, we have an estimator, and we start with that theta hat is an unbiased estimator. It needs to be unbiased, for g theta. This is somewhat a little bit more of a general formulation of estimators. So instead of estimating some parameter, this estimator estimates a function of a parameter. But of course, this function of a parameter can also be just the identity mapping. And if this is just the identity mapping, then theta hat is just an estimator for the parameter directly. It's just that, so in general, I always conceive estimators directly as estimators for the parameters. You can also understand them as estimators as functions of parameters. Sometimes useful for Kammerau bound, because it's more general. I use this as an estimator for this function of the parameter. But we will look at the special case immediately. So then the Kammerau bound states that the variance of this estimator is equal or larger than the derivative of the function g theta squared divided by the expected Fisher information. Now, if we have the identity mapping and the derivative is hence 1, so if we're in the case that our parameter estimator estimates the parameter, then the Kammerau bound states that the variance of the parameter estimator is equal or larger than 1 over the expected Fisher information. And yeah, so the right-hand sides here, these are the Kammerau lower bounds. So for the case that we are most interested in at this point, I would say that we have an estimator directly for the parameter value. We now know that the variance of such an unbiased, I shouldn't forget to say such an unbiased parameter estimator is equal to or larger than the reciprocal of the expected Fisher information, which I wrote down here. And if the variance of an estimator actually is the same as the 1 over the expected Fisher information, which of course in a concrete scenario you would have to compute, so you could try to compute the variance of the estimator, you evaluate the expected Fisher information, you find that they are the same, then you know that your estimator is really, really good because it has the lowest possible variance that it can have. And this also gives a little bit of a notion of why Fisher information is now called Fisher information, because if the Fisher information is high, so if you have a high value for j theta, then the variance is low. Otherwise, if you have a low variance, so little variability in your estimates over repeated sampling from the model, then this has a high Fisher information. So this is kind of one way to understand the term informative in Fisher information. Yeah, so that's the Kammerau bound. The question is, of course, why? Why does it hold? Where does it come from? So are there questions about this right now in terms of the theorem? No. The proof then is relatively straightforward, armed with the knowledge that we had previously and the correlation inequality. So remember that we discussed some inequalities, and one of them was the correlation inequality, which says that the covariance of two random variables x and y squared divided by the variances of each of these random variables is always smaller or equal to 1. This is called correlation inequality because this is the square of the correlation. You can also, yeah, it's the same thing as saying that the correlation is now locked in here. That the square of the correlation is always smaller than 1. Intuitively, of course, you know that the correlation is between -1 and 1, so the square is always between 0 and 1. That was the correlation inequality. If we now, for the two variables in the correlation inequality, take our score function and the estimator, then we already obtain that the variance of the estimator is larger or equal to the covariance of the score function and the estimator squared divided by the expected Fisher information, because the variance of the score function is the expected Fisher information. So this already, yeah, what we've seen previously goes in there. And then the remaining thing to do is to evaluate the covariance between the score function and the estimator. And this is done here with the Translation Theorem. So you look at the expectation of the product of score function and estimator and the product of the expectations of score function and parameter. And we already know that this expectation is 0, so we only have to evaluate this expectation. And then essentially with the same tricks that we got previously, we can simplify that to end up with the derivative of the estimator under the data. And then we know that the estimator is unbiased. That this is the expectation. So there's this is just the expectation, and then we know that it's unbiased. So because theta is an unbiased estimator for g theta, we then end up here for this covariance with this d theta g theta. And if we substitute this here, then we already have the Cramer-Rao bound. Yeah? So this is how one can. So what the Cramer-Rao bound, in a way, we will look at computing this for Gaussians in the Übung. From my perspective, what it does is that it links, it's a lower bound, that's nice, so it uses the correlation inequality to provide a lower bound, and it links the variance of an estimator in an unbiased estimator in a probabilistic model with the notion of expected Fisher information, if you want. So if you here define expected Fisher information and here define variance, then Cramer-Rao bound brings these two together. And of course, this only works because all these things are kind of similarly defined. So they have some similarities in their definitions, and this is what comes out. Essentially, you can also view this as an application of the correlation inequality to score function and parameter. But it gives you a criterion to say, okay, my estimator has a variance that is identical to 1 over the Fisher information. So first I show my estimator is unbiased, and then I find its variance is actually as large as the Fisher information. That means it's the best unbiased estimator I can find, because the Fisher information is of course not a function of estimators, that's just a function of the log likelihood function, so that's always fixed for a given model. So your estimator is good, and you can also not have a lower variance. Yeah? So that's as good as it gets for these estimators. So that's Cramer-Rao bound. That's not introductory statistics anymore, I would say. So I'm happy that I understood Cramer-Rao bound. I hope you did as well. Any questions about Cramer-Rao bound? I mean, from a practical perspective, it's like you come up with a new algorithm for estimating a parameter in a probabilistic model because you want to describe uncertainty. And then you wonder, is this actually the estimates that this algorithm generates, is this good? And then hopefully you first somehow compute its expectation, you find it's unbiased, you say, oh, that's good, but what about the variance? And then you need to evaluate the variance of your estimator. And then you say, okay, that's this variance. What can I say now? Is this a good or bad variance? And then you compute expected Fisher information for your model. And then you find, oh, my variance is larger than expected Fisher information, but not much. So it's okay. Or you find it's equal to, and then you're really, really happy. Or you get children. That also makes you really, really happy. But maybe also funny in unbiased estimators. So I don't have children, but people tell me that they get really happy when they get children. Anyway, good. Then the last thing for today, and this also fits into the last 7 minutes, if there are no questions right now, is the mean squared error. So for now we looked at bias, which is about expectations of estimators. Then we looked at definition of variance of estimators. Then we looked at a lower bound for the variance of estimators, and now with mean squared error we're essentially putting together bias and variance into one criterion, so that if we have a little bit of bias in an estimator, we can say, but it's still good because it has also very low variance or something like that. Yeah? And this comes about in this notion of mean squared error. So again, the definition is, or the setting is as previously. We have a parametric statistics model, blah, 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 estimator. And the mean squared error then is defined as the deviation of the squared deviation of the estimator from the true but unknown value to the square. So yeah, don't confuse this with the variance, because for the variance we would here have what? If we talk about the variance of an estimator. So how is the variance always defined? It's the expectation of the squared deviation of what from what? From the expectation. Yeah, which also is called, people also call that mean, yeah, but from the expectation. And here we don't have the expectation. Of course, if we have an unbiased estimator, then the true but unknown value and the expectation are the same, and then the mean square error is just the variance, which also makes sense because the bias is 0. But in general, for the mean square error, we don't have the expectation here, which then essentially accounts for the fact that the expectation of the estimator is not necessarily the true but unknown value. Yeah, so this is just how it's defined. This is basically a heads up in terms of the relation to the variance. And yeah, this is what I just said. And then one thing that you always find in machine learning books, and that also people at the MPI for human development are very interested in, is this Bias-Variance Decomposition, which is the statement that the mean squared error of an estimator is the same as the bias of this estimator squared plus the variance of this estimator. So in kind of word formula, the mean squared error is bias square plus variance. And then, of course, you can have the same mean squared error for an estimator that has high variance and low bias, and the other way around. So you can use this mean squared error as a bias variance trade-off criterion. So I allow a little bit of bias in my estimator because it has very little variance. So on average, over many repeats, my estimates don't vary a lot, which I like, but I have a little bit of bias then in my estimates. Or yeah, essentially this is how people use this and talk about this in machine learning. Small biases may be favored over large variances. So although I'm not quite estimating the true but unknown value correctly, I'm fine with that, because at least over many applications of my estimator, it's somehow not throwing me completely off. And now we almost have to finish. Now the question is, why does this hold? And this is here. So it's essentially just reform. So just I will not go over that now. So it's just starting with the definition and then modifying, doing algebra, blah blah blah, and in the end you come out at the bias square plus variance square. So there's no magic behind the mean square error and this bias square plus variance. It's just from the definition it follows, and you can use it. Yeah, so that's everything for today. So these are kind of criteria, so bias, variance, Kamarawa, mean squared error, that you can always evaluate about estimators. And when you come up with your new estimator for your new model, because you're a data scientist and you develop this new way of how to analyze data and estimate parameters, then you now have some criteria by which you can say, okay, this is a good idea or this is not a good idea. And next week we will then look at the case whether, even if, for example, you have a bias estimator, if you now assume, okay, it's biased, but I only have 10 data points. If I now would have 1 million data points, what about my bias? And these kind of things, that is what we look at next time. Yeah? Good, then see you in a bit if there are no questions in the Übung. Good, no questions. Goodbye.